get this started, and here we are. So we were talking about stress logs. You can combine data of density and sonic logs together also with laboratory measurements in order to measure or to calculate what is the plane strain modulus. If you remember, this guy was Young modulus divided y minus Poisson ratio squared. And with that, you can, based on linear elasticity and with the so-called tectonic strain equation that we have used before, you can calculate what is the horizontal stress. And this is what is called a stress log. And this is going to be very important because it's going to tell you where the hydraulic fracture has the easiest job to open up. Always going to open in the regions with the lowest minimum principal stress. And this is going to inform you how high a fracture is going to grow. For example, if you were to start a fracture at this depth over here, very likely it will grow up till it hits that high stress boundary, and it won't grow anymore until the stress is high enough next to the fracture that it can go over this bump. And the same over here. If you start a fracture over here, probably it will just be contained in this region and it won't grow until the pressure inside is high enough in order to overcome that stress. And an example of that stress log is what you saw in problem number 7 of the exam. This is an example of those stress logs, and also here you can see where this particular operator did the perforations for hydraulic fracturing. And this depends also on where you expect to have hydrocarbons as well, right? But based on these stress logs, you can help predict what is going to be the height of your hydraulic fracture. And that's something very important to know, and sometimes not very easy to predict. So now putting together what we have seen about hydraulic fracture propagation, you remember these models that we discussed over here about we can predict what is going to be the length and what is going to be the width. And now with these stress logs, we can tell what is going to be the height. Putting all these things together, we can have an idea about what is going to be, again, the width, the length, and the height of the fracture. And this is exactly what a modern hydraulic fracture simulator does. It's just this, but in 3 dimensions. So let me share with you some examples and some typical software that is used today in order to predict hydraulic fracture geometry. There is one which is called Gopher. This one is used a lot, and here also we might see some nice images about hydraulic fracture. So here you see, let me zoom in here. So here we have our wellbore, goes into the lateral, goes into the bay. Here we have the stress log, and basically what a modern hydraulic fracture simulator does is incorporate this data, which is something that you're going to calculate manually, and predict what is going to be the height and the length and the width of those fractures, and how much fluid is going to go in there, and how much proppant you should put in there. Let's see if you have, okay, here we have another image. So over here, so you see these are the vertical wells, go into the lateral, get into the formation pay. This is what this is the expected hydraulic fracture height, and usually these fake colors are the width of the fracture. So you would expect this region, red, to be the widest at this location. As you go further away, it gets thinner and thinner. But it's exactly what we have seen so far, based on the lithology of the rock, based on the stresses that you expect, and based on how much fluids you inject, you can predict what is the height and what is the length and the width of the fracture. And this is, now we have several stages, something that we're going to go in a little bit later on. You can also predict how those interact with each other. Let me show you an easier example of this, but you start getting the idea, okay? So laterals, many fractures, and what we want to predict is hydraulic fracture length, height, and width. So let me come back over here. I have an example here in the notes. Oh, I didn't upload yet the notes here, but I think I have them in Canvas. So just give me 1 sec, we'll get there. Since we're over here, guys, there is one more homework to do, and one more homework that is going to be included in the exam. So if you go into assignments, and this one is due next week on Monday or Tuesday, I believe. It's homework number 7. We're gonna go open it now. I'll come back to this in a little bit, but I wanna go somewhere else now. I have uploaded my notes for the last chapter in a PDF, but I don't think I'm gonna have time to actually write everything as I have done with the other ones. So this one is more like a set of slides. And let me download this one too. And let me go to the example I was mentioning. So we have seen all of these so far, and we have seen these as well. We have seen some of these, fracture containment, and this is the example that I wanted to talk about. And this is what the first thing that you have to do in the homework. So, and this is an easier version of what I showed just before on those examples. So here you have the plane strain modulus. This is what you calculate with the logs. And here this is the prediction that they did of the minimum principal stress, and you can see how minimum principal stress changes with depth. Here at this location you have very stiff rock, and it's consistently stiff for a high depth, and here you can see how that stress increases at that time. And at this point, what they propose in this example is to perforate these two lengths. So this is a payson. Well, actually this perforation just here, but they mean to have a hydraulic fracture that goes into this region and into that region. So let's try to predict what will be the hydraulic fracture height and which direction will grow before we actually see the result. Okay? So what do you think? We're going to start pumping in here, and this is the profile of minimum principal stress. Think about how the hydraulic fracture will grow in that location. Let's see, I think we got a few people that still don't have their exams. Anyone without exam? No? Okay. So what do you think? If you start pumping here, is the fracture going to go down? Is it going to go up? What do you think? Go up? How much? Look at, here there seems to be a spot of very low stress. So you think it's going to go up all the way, or it's going to stop over here? What do you think? Anyone else? Any suggestion? So raise your hand if you think it's going to go all the way up, or if it's going to stay there. So if it goes all the way up, any supporters? Just one? It will stay here. One supporter of that. 1 and 1, 2. So remember, the hydraulic fracture is always going to look the spots of the minimum principal stress, right? Why would it open in places with lower stress? So a modern hydraulic fracture simulator, what it does is, instead of considering this simple geometry that we have discussed before, it will consider this variation of stresses. It will consider how those stresses also increase next to the fracture, and how sometimes, even if you get stuck at the beginning with a fracture somewhere over here, after you increase the pressure a lot, it could overcome that bump and go into that direction. So let's see the result for this case. And this is what you would expect, right? So this was a plot that we had before. This is where you start the perforation. The perforation is this region, this tiny blue region over there. And as probably you expected, the hydraulic fracture starts growing up, finds this spot of very low stress. It extends a lot for some time. At the point in which the pressure here is too high, because in order to open such a long hydraulic fracture, you need to have a very high pressure, because your width, remember, is going to be the highest at the injection point. But when the pressure is too high here, it's enough to overcome this spot, and it starts growing up, and again finds another spot of low minimum principal stress, and starts growing in that direction. That's everything what the modern simulator does, and probably a few more things, but basically that's it. And here you have a cross section of what you would expect of the width, right? Perforations are here. It's very small in here, but then finds this spot of low stress and grows quite a bit, and then finds this other spot of low stress, and there opens up a lot more. But that's basically everything that goes into modern fracture simulator. So let me come back over here for a bit. If you want to know a little bit more about these simulators, I'm going to write the name of, wait a minute, I think I messed up with something. Okay, now this is still recording. So there are two very well known. One of those I show some slides, and if you go in fracturing, very likely you will use one of these. So one is Gopher, the other one is called Frac Pro. Okay, so building stress log. That's the first thing that you have to do in the homework. So let's go to the homework. You're going to have to download this file. And after you download that file, you have to calculate with depth what is based on VP and BS formulas that I'm going to upload. As I think that they are in the notes, but I'll double check. You have to calculate what is the Young modulus for that, what is the Poisson ratio. With that, you can calculate the plane strain modulus, and remember the tectonic strains and the equation for tectonic strains. From that, you have to calculate what is SH max, what is SH min, and use that to figure out what will be the expected hydraulic fracture height for a given for this given location. For problem number 2, you're going to have to use the PKN equations in order to predict what is going to be fracture length, pressure, and width for a given injection schedule. And also you're going to have to do some volumetric calculations to see how much water and how much sand has to be used for this particular location. We're going to talk a little bit about this towards the end of the lecture today. And for number 3, it's about multistage, that's where we're going, I think, right now. Okay, so let me come back over here. Okay, so we know what you have to do in this case. So we talked about the exam, we talked about the examples, talk about the notes. We need to talk now about multi-stage hydraulic fracturing. So what we have seen so far is just for one fracture. Hydraulic fracture completions of vertical wellbores have been done since the 50s. But now we are doing something else, which is multi-stage hydraulic fracturing. Basically, the concept is to take advantage of drilling a vertical wellbore in order to maximize the surface area in contact with the reservoir. Let's say that we have a pay zone somewhere over there. For a long time, in order to maximize production, we were drilling one wellbore, and if that's a vertical wellbore, that will go into the formation. Let's say that in this case, the minimum principal stress, it's in this direction, and it's horizontal. If you just do one fracture, then you will obtain a fracture coming out of the plane of the page, like this one. So that's great, right? Now, instead of having the just in contact with the reservoir, the area of the wellbore, now we have a much larger surface, which is the surface of the fracture. Well, this type of completion was done from 1950, was still done today, right? But just for the sake of maximizing hydraulic fractures, probably till 1990. But now, if we want to really maximize surface area with advances in drilling, we know that you can drill horizontal wellbores that get into the pay zone, and with that same wellbore now you can maximize the area and put many fractures in there that in its simplest conceptualization will be planar and will look something like this. So now, instead of having one fracture, you have, in this example, you have 7 fractures, right? And together with that, we have some new variables in this geometry that we can use in order to compute how much surface area we have, and how much more water and sand we need for these hydraulic fractures. So when did we start doing these type of fractures? It was actually a long time ago. I don't know if some of you, I was already born at that time, but 1990s or so, till more or less 2010, you will do this type of hydraulic fracture in which now we have an additional geometry factor, which is the distance. This is an L, okay? This is the distance between fractures. You remember that before we had length, half length of the fracture, we had height of the fracture. Well, now we have distance between fractures. And that's kind of an important parameter to which we're gonna get back in a little bit. But let me continue with this type of fracturing. So what you would do in these cases is, now if we look at the top view, this point over here is what is called the heel of the lateral. So this analogy with the foot, right? The heel is going to be over here. So this is the leg is going down, this is going to be the heel, and this, how do you think it's called? The toe, right? So this is the toe of the lateral, this point over here. And what was done in these cases, and probably still done in many parts of the world, is that you plug a section of that wellbore and you make a hydraulic fracture. Then you come somewhere over here, you plug, let me move this plug a little bit. You plug again and you make a new fracture, and so on. So this is what is called a plug and perf and fracture. So 5. So at every stage, what you would do is you plug, you perf, and you fracture, and you do one at a time. And as I was telling you, this was done until recently, and but now there are some other more modern completion procedures. So this is the length of the fracture. What else am I missing over here? I don't think anything. So just for sake of completeness, this is going to be the half length, and if we were able to make a zoom or maximize this coordinate here, remember, we'll have the width of the fracture. So that kind of makes sense, right? Instead of doing just one fracture, you take advantage of a horizontal wellbore and you do a lot of fractures. However, there are some problems with this. Can you tell me what problem you would expect from this type of operation? Or let me change the question. So this new variable, the length between fractures. Before, the height of the fracture, that's something that you more or less depends on the conditions in situ. You do not control those as much as the others. The fracture length, that depends on how much you pump. But let's assume that here you have a constant hydraulic fracture height. You cannot change that, right? But something that you could change very easily would be the distance between fractures. So what is the distance between fractures that you would want in this case? If I'm telling you I want to maximize the surface area of the fractures in contact with the pay zone, probably you would tell me, well, just put as many fractures as possible, right? But that would mean that I have to decrease this length between the fractures. But what's going to happen if you put those fractures too close? Let's say that, oh, I'm going to put those fractures every, say, 50 feet or so. What kind of problem do you think you may encounter by doing this? let's say that you put a fracture over here, and then you plug, you put a fracture, and then you want to put a fracture right next to that one. Remember that opening a fracture is going to change the stresses next to the fracture. So if I had a rock that before had a stress S3, now it's going to have some additional stress because the fracture has opened. And that additional stress is going to change the stresses near the fracture. So if you put the fractures too close, sometimes you would run into something which is called fracture interaction, in which the next fracture can actually see the previous fracture because you have changed the stresses. And if now you have more stress in this direction than what you had before, your fractures may start to deviate if you put them too close to what you had before. And if again you insist on putting that fracture too close to this one, probably now the next one, since now this one is closer to that one, is going to deviate even more and probably not grow as much as the other one. And again, if you insist putting a fracture right next to it, and if it manages to propagate, you may even run into cases in which this fracture could run into the other one. And obviously this is not good. This is not good because you're not reaching out to all the sections where you expected your fracture to go. So then this is called fracture interaction, and you want to avoid that as much as possible, because otherwise your fractures will not grow as far as you want. This additional stress over here caused by the putting a new fracture. And remember that when you open a fracture, you want to keep it open, right? Because if it closes back, then it's not going to help you much with the permeability. So what do you put inside the fractures in order to prop them open? You put proppant, right? So remember here is proppant, so that's going to force the fracture to stay open. This is also a problem of geomechanics, designing the proppant, because sometimes you put stresses that are so high it can crash, and that's not going to be good. So this additional stress is what some people call a stress shadow, but it's just an additional stress caused by deforming the rock in the subsurface. And this can lead with what is called fracture interaction, and that's not good. So very likely, if you were now to run a fracture into a region where there is no stresses or no fractures around, this one might run more or less okay, but then again you're gonna encounter these problems of fracture interaction. So the idea is to try to set this distance, which is not too close, so the fractures do not interact and can propagate well, but also not too far from each other, because otherwise you are wasting a lot of the distance of the lateral, right? This is like putting people in an auditorium. If you're going to put the right amount, not too many, not too few. Are you guys walking in May for the graduation? You're going to see that I might be there in the back, and we're very crowded, all the faculty in there. They give us a tiny space like this, and usually we aren't very happy in those tiny locations, because you put too many people in a place which is too small. And it's the same thing with this. You want to put those fractures that at the distance that they are close enough in order to maximize surface area, but not too close so they can grow more or less well into this location. So again, this type of technology that do one fracture at a time, we're talking about probably 8 years ago, 10 years ago, some other places probably 5 years ago. Some people found a solution for that, and this is actually what is in problem number 4 over here. This is the word I'm looking for, okay? Zipper style. What is that? You can sometimes get rid of these fracture interaction, or actually take advantage of those by doing what is called zipper fracturing. A zipper fracture will consist on, now instead of using just one wellbore, you use many wellbores. Let's say that you have 3 wellbores, that the 3 of them go into the pay zone, and will consist on doing fractures which are relatively far away at time number 1. Then you will do a next set of fracture at time number 2, and on the other well, which is in the middle, you will do this one only after you have done the first 2, so this one grows more or less straight in that location. Why? Because now, probably if you were to do just 1 and then 3, if this one is too close, it may not grow as much as it will grow with this other one already done. So if you add some stress in this direction by doing a fracture number 2, you add more stress in this direction. And since now you have 2 wells, you kind of do the same in those 2 wells, and this one can grow from here to there and maximize the surface area in this location. So if you were to continue again, then you will go with number 4, and then with this one in number 5. And notice that now we have one more additional length, which is important to consider in your fracture design, which is going to be the length between wellbores. So in addition to fracture height, fracture length, fracture width, now we have length between fractures, and we have length between wellbores. Very similar to the spacing between fractures. You want to choose that distance between wellbores which is close enough so you take advantage of your lease, but not too far away, but not too close, so that the fractures start running into each other. If you put the wellbores too close, those fractures are going to run into each other, and that's not going to be good. Okay, so let me add something here to complete this fracture interaction. So fracture interaction, if this is bad, will lead to narrower fractures. It could lead to non-planar fractures, and can also lead to shorter fractures. So avoiding fracture interaction is going to be good. You have a question, Michael?
Yeah, so just to clarify, for the frac,
yeah,
basically it's taking advantage of the fact that the shadow stress you said is on the same on both sides?
Yes, correct.
Okay.
Yes, you take advantage of that. So you create a shadow stress from 1, and probably if you were to do 3, it might grow like curves in this direction. Let me do it here, but I'm going to erase it. It could grow like that, but now you equalize that stress shadow in the other direction, so it might grow. It grows straight because it has the same influence in the 2 directions. Okay, so we're good with this. This technology continues to grow, and as it continues to grow, there are new types of completion. What is done today is a combination of these, but also with stages that have multiple clusters in it. So now you will do you will plug stages, and inside those stages, inside you will put clusters, several clusters in it of perforations. I'm going to make a 3D plot of what I'm drawing here, but I mean with these lines, I mean perforations. All of those are perforations. This is a single stage, and you will plug these two, and you will pump water and sand through all these clusters. Each of these is what is called a cluster, right? This is a plug, and this is your horizontal wellbore. And the concept of this new type of completion is that instead of just doing one fracture, you do many at the same time. And there are some advantages, some disadvantages to this approach. But I would say the main advantage is that you're not putting all your you're not betting, all your resources into one particular spot. Sometimes rock has a lot of variability, and just doing perforations in one particular spot, it may not be good. And also sometimes this issue of fracture interaction is not very well understood. It depends on many properties, like the stiffness of the rock or the width of the fracture. And to tell you the truth, so far we don't know very well what is the width of those fractures. We don't know if they propagate, as I'm drawing here, as single planar fractures. We know little about this. So with this approach, we're just trying to pump and trying to put our chips. I was looking for that word. I have forgotten that word. So instead of putting your chips in just in one place, you put it in many places, and you just hope to survival of the fittest. So probably if these fractures are too close, probably some of them may not grow too long. Usually you see that fractures close to the toe, if this is the injection, they grow longer than closer to the heel. But in this case, you just put lots of perforations and into a single stage, and you just hope for the best. And fractures might grow where perforations probably are done the best, where the rock is the softest, in locations where the proppant, there is no screened out of the proppant, so you can have hydraulic fractures that actually do propagate. Some of them may not, for these same issues of fracture interaction, but some of them they will, and eventually that's what is going to contribute to your surface area. So I was telling you I will do a 3D plot of this. So what you do in this case, if this is your horizontal wellbore, usually these perforations are done at an angle, and they are not exactly on the same spot, but it varies as you go along the wellbore. And let me see, probably the next one will be somewhere over there. So you put many of those, and they are at different angles. So also you're looking for the place where the perforation is going to have the minimum resistance to propagate that fracture. So let's put some numbers on this, because we have doing a lot of drawings, and actually we didn't put numbers on this. Typical completion today in the Permian Basin, more or less. I have a friend that works on this and doing data analysis, and today more or less the length of the laterals, it's about 10,000 feet. How many miles is that? Anyone knows? 10,000 feet? It's pretty long, right? Can anyone tell me? Actually, let's see. How
1.89.
How many?
1.89.
1.89. Well, let's say 2 miles. Okay. It's pretty long, right? Lateral of 2 miles long. In each of those laterals, you have about 40 stages. So 40 of these stages in this lateral. In each stage, you usually have from 4 to 15 clusters. So remember the clusters are those ones. In this particular stage, I made a schematic for 5 clusters. You may say, well, more clusters, the more clusters the better. But you know, it takes some resources to do those clusters, and there is some data that suggests that too many clusters facilitates what is called a sand screen out. That most of the sand goes just into the first fractures and it doesn't get to the fractures towards the end of the stage. So although at some point people were trying with lots of clusters, now people are going back to less clusters, but you guarantee that most of those are going to be open. It's not guaranteed. There is some data that says that only 60% of the clusters are open. Remember, in this case, as I was telling you before, just putting a lot of clusters, but you don't know if actually all of those are going to have fractures or not. Okay, so 40 stages, 4 to 15 cluster per stage. In each cluster, you have about 6 perforations per foot, and usually these ones are done at an offset of 60 degrees. So in my drawing over here, probably the offset was less than that, was 30 degrees or 45 degrees. Usually this offset can be a little bit bigger, like 60 degrees. And let's get into numbers of water and sand now. For each of these completions, what is done today, it's more or less 2 barrels per minute per perforation. And more or less, if you put these numbers into a typical stage, you will have for each stage about 100 barrels per minute of injection. And also, if you put these numbers into typical lengths, you will have about 2,500 gallons per linear foot of horizontal wellbore. This is this LF. Let me move this up. So this is per linear foot of horizontal wellbore. And also typical proppant numbers are 2,000 pounds of proppant per linear foot, again, of horizontal wellbore. So probably you can see now that this is a lot of water and it's a lot of sand. And in the homework, you're going to have to do a calculation for just one fracture, and you will see that this can amount to several swimming pools and several tracks of sand. Let's do a small exercise. I've been talking a lot, so I like that you do an exercise. I like that you tell me if I had a mixture of sand and water, what is going to be the percent of volume of sand and volume of water with these typical numbers. So we're saying that per each linear foot of a wellbore, I'm injecting 25 gallons of water or fracturing fluid, and I have 2,000 pounds of proppant. So can you tell me what is going to be the volume fraction of sand to water for this particular example? I like that we do this because I want to show you an example about proppant schedule, but I like that you compute that number on your own, okay? So I'll give you 3 minutes for that. I'll give you a hint. You can use 2.75 as the density of proppant. So with that, you should be able to calculate volume, and probably you may convert those gallons to I think the easiest will be meter cube, and then you have volume divided by volume, you'll get volume fraction. Just for you as a reference, this is about 60 barrels per linear foot. Okay, probably that's a little bit easier to picture in your mind, other than 2,500 gallons. This is about 60 barrels. Anyone has the answer? Actually, I did it with liters. With liters is easier.
Like 3%.
How much?
3?
3%?
Yeah.
Are you sure? Let's try to check that number.
Is the density of proppant 2.75 pounds per gallon?
No, 2.75 grams per centimeter cube, or 2.75 kilograms per liter. So as you solve that, let me tell you a little bit more about this hydraulic fracturing business. As you see, some of these numbers, they are very common, and some people say that what is done today is manufacturing, meaning that with manufacturing you'll do an industrial process which is repetitive, which is meant to, in order to minimize cost, to do always the same. Well, with fracturing, although there are advances in order to keep up with production, a lot of companies, they do this manual fracturing, just repeating the same design over and over, of course in the same place, right? If you go to a different location, you have to change your conditions. You have a number, Jason?
Yeah, I got 3% too.
3%? You got 3%?
Yeah. No, like,
Okay, but did you convert that to volume?
gallons per foot would be volume.
No, but I like to see in terms of, say, gallons of sand per gallons of water. So let me show you what I did, okay? Then probably you can do this number on your own later on. 2,000 pounds per linear foot divided 2,500 gallons per linear foot. I convert this to liters. Okay, first I do this number, then this pound is going to be equivalent to 0.3 liters of sand, and this 1 gallon is 3.8 liters. And so if you multiply these two, okay, I think I missed something here. What is 0.3 divided 3.8? That's the 8%, right? Times that 0.8 is going to be actually a little bit less. It's going to be about 6% volume per volume.
Not like 7.8%.
Okay, yeah. Okay, with 7, 6. So this is a ratio that I want you to picture in your mind, right? If you were looking at the mixture right now of sand and water being injected, about 8% of that is sand. So this is a mixture where 90% of water is water and more or less 10% is sand. And that's what is in what is called the injection schedule. So if you were to inject proppant and water, usually at the beginning, let's say this starts from 0, you start injecting, and at some point also you're going to stop injecting. This will be the total amount of injected fluid, but your proppant is not going to go from the very beginning. Your proppant is going to be 0 at the beginning. You don't want any proppant at the beginning. You want to open the fracture, okay? Because it might screen out at the tip, and that's not good. So first you want to open your fracture. This is what is called the path, and then you start to escalate your injection of proppant. So this will be the proppant, and according to the numbers that we have done, this is about, in volume, is about 10%. Okay, so this is what is called the injection schedule. And let me show an example of that. If you go to the homework, I strongly recommend, you don't have to do this, okay, but I strongly recommend, if you're interested in this topic, that you check this link. It goes into an article from Schlumberger. Actually, if you run into these oil field review articles, usually they are very good, very well written. And this one is about microseismicity, which is what we're going to talk in the last 10 minutes of the lecture. But let me see what is going on here. I want to show an example of injection schedule, and then we'll come back. Okay, here we go. You see, this is a typical injection schedule. Here you have the pump rate in blue, and here you have the proppant concentration. When you start injecting, you have no proppant, of course. This is what we said is the pad, and as you start opening more fracture, then you start injecting proppant. And if you look at the proppant concentration, is about, you can also calculate these numbers from what we did before. And this one is about 1 pound per gallon. And according to our numbers before, let me come back to that. Another one. $2,000, let's say, divided 2,500. That's, these two numbers also give you 0.8 pounds of proppant per gallon of fluid. So very similar to the numbers that you see in that proppant schedule. Okay, so now we know the geometry for multistage hydraulic fracturing. We know they interact with each other, and we know that how to inject the proppant in the fractures. I want to emphasize, and this is very important, that all of these schematics sometimes that's an idealization of what we expect it happens in the subsurface. But up to today, I believe that nobody knows what is going on really over there. We have some clues, but still there is a lot of learning to be done in this hydraulic fracture business, and to see if you get something like this or something which is actually more complex. And actually, that information that these hydraulic fractures might be more complex than what we think, and that what this schematic shows, comes from what is called microseismicity. In microseismicity, you monitor the seismic activity generated by hydraulic fracturing. And it turns out that, let's say that we have a horizontal wellbore in which you do multi-stage hydraulic fracturing. Let's say that in this case we're just going to have single clusters, one here, one there, another one here, another there. You would expect fractures to form planar and long, like these ones. Let's say that there is no significant fracture interaction. With microseismicity, what you can see, and that's actual data, that there is a lot of micro earthquakes that come from close to the fracture, and are these dots that I'm drawing over here. But there's some other activity that actually may come from far away from the fracture. Each of these dots, it's a micro earthquake. And what it would be a micro earthquake? A micro earthquake would be an event in which we have a fracture that slides in shear, and when it does that, it generates elastic waves that can be measured with geophones that usually placed on surface, and also on some other wellbores next to the ones that you are monitoring. You guys remember what the Richter scale is? The Richter scale quantifies the amount of a seismic moment, and it goes with letter M, and the magnitude of that moment is usually, there is a formula which is very nice that tells you that that magnitude is proportional to the stiffness of the rock and proportional to the amount of injected volume. But this M, remember, is the same of the Richter scale. And if you remember the Richter scale for earthquakes, usually we say that there is a very bad earthquake when M is equal to 7, 8. Sometimes even if you don't have good buildings, 6 could be a lot of damage. But in microseismicity, usually M is less than 0. Remember, this is a logarithmic scale. So you can have values less than 0. So the magnitude is going to be -1, -2, -3, sometimes smaller. But remember, each of these events is shear fracture reactivation, something we have already seen. The stresses are high enough that produce this fracture or fault to slide, and that slide is what releases all this seismic activity. So if you do fracture 1, probably you get a cloud of points like that. If you do stage number 2, you may get another cloud like this one. And what this cloud is suggesting, as you see over here, that this comes from additional fractures, is that many of these formations, they are actually either already fractured, or when you do hydraulic fracture, they also break in shear a little bit. And that shear is what creates a microseismicity, and these reactivated fractures are the ones that eventually connect and create additional flow paths for oil and gas to go from the reservoir into the big fractures. There are many studies that show that if you just had one single planar fracture, as the one that we have been showing so far, which 3D version will be that, you cannot justify the production rates you see in wellbores. There is something else there that is helping the gas and oil to come to the wellbore. And those are these additional microfractures. That's why it's very important to know what is the faulting regime and what is the potential and likely orientation of natural fractures, because those are the ones that are going to help you produce more out of these very tight formations. Sometimes with hydraulic fracturing also, if you run next to a fault, and this is something which we have already seen, what happens when we inject fluids next to a fault? Anyone remembers? We didn't talk much about this, so I'm going to repeat it. When you inject fluids too much too close to a fault, you increase the pore pressure, you decrease effective stresses, and you can reactivate this fault. In all these cases, this small one and this big one, what injection is doing is moving the Mohr circle that was originally something over there into this direction, into the direction of shear. When it gets to the shear line, it creates all that microseismicity. So if you were to put the fracture now into this location, very likely will run into the fault and will create not only activity, microseismic activity next to the fracture, but also microactivity very close to the fault. Because remember, all of these microseismicity, most of it's all shear fracture reactivation, and probably that the moment or the magnitude of that microseismicity next to a fault is going to be quite bigger than next to the hydraulic fractures. So this additional tool of microseismicity is going to allow us to see more or less indirectly where the hydraulic fractures are going, not only in the lateral direction, but also in the vertical direction. They can tell you the height. And what time is it, guys? I think I see your faces like I'm running out of time. Where's my phone? Here. Okay, I'm right on time, but so you have to use these concepts in order to solve this problem over here. So this is an example of microseismicity in which I want you to interpret mostly the geometrical properties of this hydraulic fracturing job. What is the length of the laterals? What is the distance between wellbores? What you expect the length of the fractures, the half length of the fractures, and what is the length between stages. I think with this you have everything you need to solve the homework. Guys, remember the exam we say Thursday evening, right? So no issues with that. Prepare for that. These two homeworks are the ones that are going to be included in the exam, and it's going to be very similar to the other exams. Since this one is a final exam,